how the data offline sync capabilities work in Oracle Mobile Cloud Service for the server wins collision detection and resolution features, this episode is the one for you. G'day, I'm Chris Muro from the Oracle Mobile Platform team. In the previous episodes, we described the three options the client SDK has for resolving conflicts: clients wins, server wins, and preserve conflict. Now, the focus of this episode is the server's wins option. This option states when the client sends an updated object to the server, if the server detects a conflict, in this scenario it is assumed the server will ignore the client's updated object in preference of keeping its own updated object that it already has. And the client SDK will remove its updated object with a copy of the server's object. There is no recourse for the client in this scenario. Its updated object is always overwritten with the server's updated object. With this in mind, let's now consider, like we did in the last episode, the three scenarios that need to be taken care of. That is, creating an object, updating an object, and deleting an object. The first scenario is the create scenario, where on the mobile client, the client is creating a new object to save to MCS. Now, the great thing for you, and specifically more for me as a teacher, is there's nothing new to learn here. In this case, the scenario is exactly the same as the client wins create. As the server doesn't have the object, the client object will always get created on the server side in this case. So then let's consider the server wins policy when the user updates a record on the client. Like previous, the mobile programmer will use the endpoint API to retrieve an object from the local cache, update it, and then save it. In doing this, the endpoint API will form a put request to the server with a copy of the object to update on the server. However, importantly, in the server wins scenario, it would also include the if match header with a copy of the object's e-tag that was fetched when the object was originally synchronized from the server. The if match header and e-tag value is very important, as it indicates to the server that this isn't a client win scenario where the client's update should overwrite anything on the server side. Rather, this is a server win scenario where the specific if match e-tag value will be used by the server to determine what to do, and we're going to describe that next. So, for a put containing an updated object, in this case the server-side programmer in the custom API must detect if the if match header with an e-tag value is present. Then, when the object has been submitted from the client, we use its ID to determine if it has already been stored previously on the server. If we discover it doesn't, we return a 404 error, and the client SDK will automatically remove its copy of the object. So remember, the server wins here, and the server is saying that the object no longer exists, and the client, by saying server wins in its own options, follows this rule religiously. However, alternatively, on the custom API side, if we discover that the object does exist on the server side, the server then needs to work out what to do. If the e-tag that the client supplies in the if match header matches the e-tag of the server-side object, this implies no other user has updated the object since the client originally took a copy. In this case, it is okay for the client-side updated object to overwrite the server-side object. In doing so, the server will need to update the server-side e-tag for the object and return that in the response to the client with a successful status code, though the location header with the new object ID in this case isn't required as the object already exists. Separately, if the server discovers that the client copy of the e-tag does not match the server-side copy of the e-tag for the object, this implies since the client took a copy of the server-side object and its e-tag, somebody else has updated the server-side object and its e-tag, and by inference, the changes occurred and that we weren't aware of. Because this is a server win scenario, what the server needs to do in this scenario is reject the change of maintaining the copy of the object, the client's copy of the object on the server. In turn, it must send an error status code of 412 back to the client to indicate that the server has rejected the change, as well as the e-tag and copy of the updated server-side object. In this case, the client SDK automatically detects this scenario and will update the client's local copy of the object and e-tag with what the server provided in the 412 error response. This just leaves the delete scenario for server wins. Now, as you can guess, once the client retrieves, deletes, and saves the changes via the endpoint API on the client, the endpoint API will send a delete HTTP request with the URI of the resource and a HTTP header if matched with the e-tag of the client-side object. What the server-side custom API must then do is again detect the presence of that if match header with an e-tag value. In finding this, next, if the server-side code discovers the object doesn't exist on the server side using the ID of the object passed in the URL, given the client was asking for the object to be deleted, then there's really nothing to do. Job done, just send a successful result. Alternatively, the object is found to exist on the server side, and the custom API discovers the client object's e-tag and the server object's e-tags match, this implies nobody has updated the object on the server since the client took a copy, so again it's okay to delete the object server side. This will again result in a successful response back to the client. Finally, if the object is found to exist server-side, but this time the server discovers the e-tag doesn't match, this implies another user has subsequently updated the server-side object since the client took a copy. And as this is a server win scenario, the server-side copy of the object should remain and not be deleted. Similar to the failed put operation, what the server needs to do in this scenario is reject the delete, maintaining the copy of the object on the server. In turn, it must send an error status code of 412 back to the client to indicate that the server has rejected the change, as well as the e-tag and copy of the updated server-side object. Again, the client SDK will automatically detect this scenario and will update the client's local copy of the object and e-tag with what the server provided in the 412 error response. So much like client wins, from the mobile client developer's perspective, they're simply creating, updating and deleting objects on the server. And with a simple save, the client-side SDK takes care of the rest of the work for them. However, it's up to the server-side developer to write a custom API that understands the scenarios and acts appropriately to the client's needs. So stick with us for the next episode where we'll discuss the last option, preserve conflict.